Chapter 18, Tools of Ridiculous Precision. Some scientists and science teachers can be very exact. They may take points off a test score if the sixth decimal place in your answer was rounded incorrectly. They may tuck in their periodic table t-shirt and insist on correcting those who say wait when they meant mass. And they may make everyone, including themselves, wear goggles even when mixing sugar water. Now try to imagine someone whom this scientist would hate for being even more fussy. That is the kind of person who works for a Bureau of Standards and Measurement. Maintaining measurements. Most countries have a standards bureau whose job it is to measure everything. To scientists who work at standards bureaus, measurement isn't just a practice that makes science possible, it's a science in itself. For historical reasons, France's Bureau International des Poids des Mesures, BIPM, and I don't really know how to say that, just outside Paris, acts as the boss of all the other standards bureaus, making sure all the franchises stay in line. One of the more wacky jobs of the BIPM is looking after the international prototype of the kilogram, the world's official kilogram. It's a 2-inch wide, 90% platinum cylinder that by definition has a mass of exactly 1.000000 kilogram, to as many decimal places as you'd like. I'd say that's about 2 pounds, but I'd feel guilty about not being exactly right. Because the international prototype of the kilogram is a physical object and therefore may be damaged, and because the definition of a kilogram has to stay constant, the BIPM must make sure it never gets scratched, never attracts a speck of dust, and never loses, the Bureau hopes, a single atom. So they constantly monitor the kilogram's temperature and the pressure to prevent microscopic changes and any stress that could knock off even a single atom. And the kilogram is made from dense platinum and iridium element 77 to minimize the surface area exposed to dirty air. Platinum also conducts electricity well, a property that cuts down on the buildup of static electricity that may zap some stray atoms. Finally, platinum's toughness helps prevent the chance of a disastrous fingernail scratch on those rare occasions when people actually need to lay a hand on the kilogram. Other countries need their own official 1.000000 cylinder to avoid having to fly to Paris every time they want to measure something precisely, and since the kilogram is the standard, each country's copy has to be compared against it. The process of comparison to make sure everything is exactly correct is called calibration. The United States has its own official kilogram, called K20, i.e. the 20th official copy, which is kept in a government building in Maryland. Usually, the BIPM uses one of 6 official copies of the kilogram, each kept under 2 bell jars to calibrate the copies. But the official copies have to be measured against their own standard, the original, so every few years scientists remove the kilogram from its vault, using tongs and wearing latex gloves, of course, and not holding it for too long because a person's body temperature would heat it up and ruin everything, and calibrate the calibrators. Alarmingly, scientists noticed during calibrations in the 1990s that even accounting for atoms that rub off when people touch it, in the past few decades a kilogram had lost an additional mass equal to that of a fingerprint, half a microgram per year. No one knows why. The failure to keep the kilogram perfect is worrying, and it would be best if we could get rid of the cylinder altogether. Science owes much of its progress since about 1600 to using a non-human-centered point of view about the universe. The kilogram is one of 7 base units of measurement used in science, the others being the ampere, the candela, the meter, the Kelvin, the mole, and the second. And it's no longer acceptable for any of those units to be based on a human-created object, such as the platinum and iridium cylinder, especially if it's mysteriously shrinking. The kilogram conundrum has become an increasing source of international worry and embarrassment, at least for the people who make it their business to worry about such things. The pain is even worse because the kilogram is the last base unit that is connected to a physical object. A platinum rod in Paris defined 1.000000 meter through much of the 20th century until scientists redefined it with a krypton atom in 1960, fixing the meter as being 1 1,650,763.73 wavelengths of red-orange light from a krypton 86 atom. This distance is virtually identical to the length of the old rod, but it meant that the old rod could be scrapped, since that many wavelengths of krypton light would stretch the same distance in any vacuum anywhere without having to worry about handling a physical object. Since then, measurement scientists, metrologists, have redefined a meter as the distance any light travels in a vacuum in 1 over 299,792,458 of a second. In the same way, the official definition of 1 second used to be about 1 over 86,400ths of one spin on Earth's axis, 86,400 being the number of seconds in one day, but a few pesky facts made that an inconvenient standard. Most important, the length of a day is slowly increasing because of the sloshing of ocean tides, which drag and slow Earth's motion. To correct for this, meteorologists slip in a leap second about every third year, usually when no one's paying attention, at midnight on December 31st. But that's an ugly solution, so the U.S. Standards Bureau has developed cesium-based atomic clocks to define the second instead. Atomic clocks run on the same leaping and crashing of excited electrons we've discussed before. Each cycle of jumping up and down always takes the exact same, extremely short, amount of time, so the atomic clock can measure time simply by counting the light rays that are released as the electrons move about. Element 55 proved to be a convenient one for use in atomic clocks because it has one electron exposed in its outermost shell with no nearby electrons to mess up the process. Cesium's outer electron is fast. Instead of a few dozen or a few thousand times per second, it performs 9,192,631,770 back and forths every 1 Mississippi, and the time that it takes for those 9,192,631,770 flip-flops is now fixed as the official standard for 1 second. A changing constant. Scientists love constants. The charge of the electron, the strength of gravity, the speed of light. No matter the experiment, no matter the circumstances, those values never vary. If they did, scientists would have to throw out the precision that separates hard sciences from social sciences, such as economics, where human behaviors and human idiocy make universal, unbreakable laws impossible. Even more interesting to scientists are what are known as fundamental constants. Obviously, the numerical value of your height or weight or anything else would change if we suddenly decided that meters should be longer or if the kilogram suddenly shrank. Fundamental constants, however, don't depend on measurement. The best known of these fundamental constants is called the fine structure constant, which is related to electrons. In fact, it controls all kinds of processes within atoms. In fact, if alpha, that's what scientists call the fine structure constant, had been slightly smaller right after the Big Bang, nuclear fusion in stars would never have gotten hot enough to create carbon. Also, if alpha had grown slightly larger, all carbon atoms would have disintegrated long before finding their way into us. Why didn't it get too big or too small is, as physicist Richard Feynman once said, one of the greatest mysteries of physics, a magic number that comes to us with no understanding by man. You might say the hand of God wrote that number, and we don't know how he pushed his pencil. Historically, that didn't stop people from trying to work out a value for the fine structure constant. English astronomer Arthur Eddington grew fascinated with alpha. Eddington believed that some numbers had supernatural significance, and in the early 1900s, after alpha was measured to be around 1/136th, Eddington began making up proofs that alpha equaled exactly 1 over 136, partly because he found a mathematical link between 136 and 666, aka the sign of the beast, a number associated with the devil. Later measurements showed that alpha was closer to 1 over 137, but Eddington just tossed a 1 into his formula somewhere and continued on. This earned him the nickname Sir Arthur Adding 1. Today, alpha equals 1 over 1 37.0359 or so, and its value makes the periodic table possible. It allows atoms to exist and also allows them to react with sufficient energy to form compounds, since electrons neither roam too far from their nuclei nor cling too closely. This just right balance has led many scientists to conclude that the universe couldn't have hit upon its fine structure constant by accident. Those who prefer theology, the study of religion, over science, say alpha proves that a creator has programmed the universe to produce both molecules and possibly life. That's why it was such a big deal in 1976 when a Soviet, now American scientist named Alexander Schlechter visited a place in the African nation of Gabon called Oklo and declared that alpha was getting bigger. Oklo is the only natural nuclear fission reactor known to exist. It stirred to life some 1.7 billion years ago, and when the French found the site in 1972, it caused a scientific roar. Oklo is powered by nothing but uranium, water, and blue-green algae, i.e., pond scum. Really. Algae in a river near Oklo produced excess oxygen after undergoing photosynthesis. The oxygen made the water so acidic that as it trickled underground through loose soil, it dissolved the uranium from the rocks below. The uranium became concentrated in one spot, achieving a critical mass, and the water helped to slow down neutrons enough to make the nuclear fission occur. Of course, fission also produces heat, and the reason there's not a big hole in Africa at Oklo today is that when the uranium got hot, it boiled the water away. With no water, the process ground to a halt. Only when the uranium cooled down did water trickle back in, which restarted the reactor, and the cycle repeated. How did scientists work all this out 1.7 billion years after it happened? With elements, of course. Elements are mixed thoroughly in the Earth's crust, so the ratios of different isotopes should be the same everywhere. At Oklo, the uranium-235 concentration was 0.003 to 0.3% less than normal, a huge difference. In addition to that odd observation, there was an overabundance of useless elements such as neodymium, element 60. Neodymium mostly comes in 3 even-numbered flavors, isotopes with masses of 142, 144, and 146. Uranium fission reactors produce odd-numbered neodymium at higher rates than normal. In fact, when scientists analyzed the neodymium at Oklo and subtracted out the natural neodymium, they found that Oklo's nuclear signature matched that of a modern man-made fission reactor. Amazing. Still, if neodymium matched, other elements didn't. When Schlechter compared the Oklo nuclear waste with modern waste in 1976, he found that too little of some types of samarium had formed. By itself, that's not so thrilling, but again, elements such as samarium don't just fail to form. So the missing samarium suggested to Schlechter that something had been off back then. He calculated that if the fine structure constant had been just a fraction smaller when Oklo went nuclear, the differences would have been easy to explain. The problem was alpha is a fundamental constant. It can't vary, not according to physics. With so much at stake, many scientists since 1976 have challenged the alpha-Oklo link. The changes they're measuring are tiny, and after 1.7 billion years, it seems unlikely anyone will ever prove anything about alpha using Oklo data. But again, never underestimate the value of throwing an idea out there. Schlechter's samarium work whetted the appetite of dozens of ambitious physicists who wanted to knock off old theories, and the study of changing constants is now an active field. Where is everyone? We've already met Enrico Fermi under rather poor circumstances, since he won a Nobel Prize for discovering elements he didn't actually discover. But it isn't right just to leave you with a negative impression of him. Scientists loved Fermi universally and without reserve. He's the namesake of element 100, fermium, and he had a devilishly quick mind as well. During scientific meetings with colleagues, they sometimes needed to run to their offices to look up equations. Often as not, when they returned, Fermi, unable to wait, had derived the entire equation from scratch and had the answer they needed. Not even Fermi, however, could wrap his head around one simple question. As noted earlier, many philosophers marvel that the universe seems fine tuned to produce life because certain fundamental constants have a perfect value. Moreover, scientists have long believed that Earth is not special. Given that ordinariness, as well as the infinite number of stars and planets, and the amount of time that has passed since the Big Bang, the universe should really be swarming with life. Yet not only have we never met alien creatures, we've never even gotten to hello. As Fermi thought about those contradictory facts over lunch one day, he cried out to his colleagues as if expecting an answer. Then where is everybody? His colleagues burst out laughing and at what's now known as Fermi's paradox. But other scientists took Fermi seriously, and they really believed they could get at an answer. The best known attempt came in 1961, when astrophysicist Frank Drake laid out what is now known as the Drake equation. In short, it's a series of guesses about how many stars exist in the galaxy, what fraction of those have Earth-like planets, what fraction of those planets have intelligent life, what fraction of those life forms would want to make contact, and so on. Drake originally calculated that 10 such civilizations exist in our galaxy, but again, that was just an informed guess. How on earth, for instance, can we figure out what percent of aliens want to chat with us? Nevertheless, the Drake equation is important. It outlines what data astronomers need to collect, and it put astrobiology on a scientific foundation. Perhaps someday we'll look back on it as we do early attempts to organize a periodic table. And with vast improvements recently in telescopes and other measuring devices, astrobiologists have tools to provide more than guesses. In fact, the Hubble Space Telescope and others have collected so much information from so little data that astrobiologists can now go one better than Drake. They don't have to wait for intelligent alien life to seek us out. Rather, they may be able to measure direct evidence of life by searching for elements such as magnesium. Obviously, magnesium is less important to life than oxygen or carbon, but element 12 can be a huge help for primitive creatures, allowing organic molecules to turn into real life forms. Almost all life forms use metallic elements in small amounts to create, store, or move energetic molecules around inside them. Animals use iron and hemoglobin, but the earliest and most successful forms of life, especially blue-green algae, used magnesium to drive photosynthesis. Photosynthesis, the conversion of sunlight into sugars, is the basis of the food chain, and the key molecule in this process is chlorophyll, which has magnesium ions at its center. Magnesium on planets also suggests the presence of liquid H2O, another substance crucial for life to exist. Magnesium compounds sponge up water, so even on bare rocky planets like Mars, there's hope of finding bacteria. On watery worlds like Jupiter's moon, Europa, magnesium helps keep oceans fluid. Europa has an icy outer crust, but there are huge liquid oceans beneath that, and satellite evidence suggests that those oceans might be full of magnesium salts. Magnesium compounds, among others, can provide the raw materials to build life. Detecting magnesium salts on a bare, airless planet is a good sign that perhaps some life form may be there. Even though the hunt for alien life has grown more sophisticated, it still relies on one huge assumption, that the same science we study on Earth holds true in other galaxies, and that it held true at other times. But if alpha changed over time, then perhaps life started effortlessly when alpha relaxed enough to allow stable carbon atoms to form, and without any need for a creator. Some physicists, using Einstein's theories, believe that alpha variations over time could mean alpha variations across space. According to this theory, just as life arose on Earth and not the moon because Earth has water and oxygen, perhaps life arose here on a random planet in an unremarkable pocket of space because only here does alpha have the correct value for stable atoms and full molecules. This would answer Fermi's paradox. Nobody has come calling because nobody's out there. Astronomers now know of thousands of planets, which makes the odds of finding life somewhere else quite good. Still, the great debate of astrobiology will be deciding whether Earth and human beings have a special place in the universe. Hunting for alien life will take every bit of measuring genius we have, possibly with some overlooked box on the periodic table.